Okay, so now let's look at another type of circuit that we can analyze with our node voltage method. So in this circuit, we see we have a dependent source, and so that's indicated by this diamond shape here, as opposed to our circular shape for our independent source. And so in this case, we have a dependent current source, which is dependent on current Ix, which is defined somewhere else in the circuit. Of course, this could have also been dependent on some voltage. It could have also been a voltage source that's dependent on a voltage or current somewhere else in the circuit. What we're going to talk about here applies to any type of dependent source. In this case, we're trying to find the values of these node voltages, V1, V2, and V3. And this is an example from page 86 in the textbook. And so notice here, steps 1 and 2 have already been done for us. So they've already identified our essential nodes. They've chosen the bottom one to be our reference node. And they have also labeled our node voltages. What you might consider doing for some extra practice, if you want, is you could define your reference node at a different essential node, redefine your node voltages, and solve to see if you get the same thing. Well, of course, in this case, the node voltage values might be different, but you could see if, for instance, the current through the 3 ohm resistor is the same. Okay, so we're going to see having these dependent sources only makes a slight difference to our analysis technique. So the only difference is that we're going to add an equation for each dependent source that we have. So only difference is we add one equation for each dependent source in the circuit. And so it's worth pointing out that it's one equation for each dependent source. So if we, in this case, we only have one dependent source, so we're only going to be adding one equation. So we know that we have, for instance, our n sub e equals 4 in this case, because we have up here, we have 1, 2, 3, 4 essential nodes. So that means n sub e is 4, and we know in general, we have 4 minus 1 equals 3 equations. So this is n sub e minus 1 is our number of equations. But now, we say we have one dependent source, so we say plus 1 dependent source means that we are going to have 4 equations that we need for this circuit. So let's take a look at where these equations are coming from. So as you might guess, our first 3 are going to be the same as what we've seen before: an equation for node 1, an equation for node 2, and an equation for node 3. So let's go ahead and write those out. So for node 1, and so like I've done with the past couple examples, I'm not going to write out each step explicitly, but if you're still having trouble seeing any of these steps, please don't hesitate to contact me and I'd be happy to go through each step in more detail. So for node 1, we're over here on the left and we're looking at current going out the top, the right, and the bottom. So our current going out the top is going to be V1 minus V3 over 2 ohms. So V1 minus our adjacent voltage V3 divided by resistance connecting them, which is 2. Our current going out the right is going to be V1 minus V2 divided by 3. And then our current going out the bottom is negative 4. And so the reason that is a negative is because, again, by definition or by convention, we're defining our currents as leaving. So this current going out the bottom is actually coming in, which means it's negative. So we have negative 4. So there's our node 1 equation. And so in this case, I'm just going to collect terms without getting rid of our fractions. So we can say we have 1/2 plus 1/3 times V1. We have plus a negative 1/3 times V2. And we have plus a negative 1/2 times V3. And that's equal to 4. So that's our node 1 equation with our terms collected. So now let's do our node 2 equation. So for node 2, we have a current going out the left, the bottom, and the right. So we can just draw those in real quick. So of course we have this, something like that. So we have a couple options here. So this current out the bottom, we can go ahead and leave that as Ix, or we could write it as V2 over 4, either way. So I'm going to actually do it different than what it shows up in the notes posted online, just so you can see how that works either way, and hopefully I don't get myself in too much trouble here trying to do that on the fly. So what we have for current going out the left, we're going to have V2 minus V1 over 3. So V2 minus V1 over 3. For our current going out the bottom, we said we can just call that Ix. So we have plus Ix. In this case, it's positive because the Ix is leaving. And then our current going out the right is a negative 4Ix. So we have minus 4Ix. And that is equal to 0. Okay, so we can again sort of collect terms here. We have a negative 1/3 times V1. We have, we're not going to have anything times V2. Well, no, sorry, we do have V2. We have a 1/3 times V2. And we don't have anything times V3. And then we have a minus 3Ix, which is equal to 0. So let me go ahead and put this on the side so we don't forget these terms. But notice over here we have 0 times Ix in our node 1 equation. And here we have 0 times V3 in our node 2 equation. Okay. So now let's move on to our node 3. Okay, so for node 3, again, we have our currents conventionally as leaving this node, so one going up, one going left, one going down. So our current going up is going to be V3 minus V1 over 2. So V3 minus V1 over 2. And our current going out the left is going to be 4Ix, just because that's the value of that current source. So plus 4Ix. And then our current going out the bottom from Ohm's law is just going to be V3 over 6. Plus V3 over 6, and that's equal to 0. Okay, so we can collect our terms again. So we have a minus 1 over 2 times V1. We have nothing times V2. We have a 1/2 plus 1/6 times V3. And we have plus 4Ix. So again, let's just put a little note over here so we don't forget this was 0 V2 for this equation. Okay, so that's where our first 3 equations come from, but notice we said we need 4. So our fourth equation is actually going to come from the constraint on our dependent source. So we're going to call this fourth equation our dependent source constraint equation. And so basically what we're going to do is we're going to say, all right, this dependent source depends on Ix. So we go back to the circuit and we say, where is Ix? Well, Ix is right here. So now we want to put this Ix in terms of our node voltages. So we want to put, in this case, Ix in terms of node voltages. And in this case, our node voltages are V1, V2, V3. It doesn't have to be all, so long as it's at least 1. And in this case, it's pretty simple because we almost use this in our node 2 equation. So we said this current going down through this resistor is just V2 over 4 from Ohm's law. So we can say Ix is V2 over 4, and we can rearrange that a bit and say that is V2 minus 4Ix equals 0. So in this case, notice that we have 0 times V1 and 0 times V3. So neither of those terms are in this equation. So again, you have some options here with your solution method as far as whether you would prefer to do substitution or linear combination. As I keep pushing, I think that matrix method is the better method just because it scales up nicely to more complex circuits. So in my variable matrix now, I have V1, V2, V3, but I also have our current Ix, because that's going to be our fourth unknown. Notice we have 4 equations with 4 unknowns, V1, V2, V3, and Ix. So I can define each equation such that I'm writing it as coefficient V1, coefficient V2, coefficient V3, coefficient Ix. That way I know where to put terms in my coefficient matrix. So from this first expression for node 1, we have our 1/2 plus 1/3 our minus 1/3, our minus 1/2, and then 0 times ix. So what that looks like down here is 1/2 plus 1/3, negative 1/3, negative 1/2, and then 0 being multiplied by our ix. So this matrix is going to be inverted, and our constant from that top one was going to be 4. So that just comes from the right side of our equation in our node 1 equation. So now for our node 2, you can just barely see it on the top of the screen there. We're going to have a negative 1/3 times v1, a 1/3 times v2, a 0 times v3, and negative 3 times ix. And so this is going to look a little bit different from what's posted in the notes online, and that's just because we defined this current a little bit differently. We defined this current a little bit differently. But of course, both are going to give us the same answer. For our coefficients in our third equation, we have negative 1/2 times v1, we have 0 times v2, 1/2 plus 1/6 times v3, and 4 times ix. And then finally, for our dependent source constraint equation, we have 0 times v1, 1 times v2, 0 times v3, and minus 4 times ix. And I forgot to put these, but of course our node 2, node 3 independent source constraint all have zeros in our constant matrix. So if we plug this in, we actually get some nice numbers because it's a textbook example. So we get 32 volts, negative 25.6 volts, we get positive 62.4 volts. So those are our 3 node voltages, V1, V2, and V3. And then we find that Ix is negative 6.4 amps. So of course we could write down here that our V1 was 32 volts, our V2 is equal to negative 25.6 volts, and our V3 is equal to 62.4 volts. Okay, so that pretty much covers all the different types of examples we're going to look at for node voltage. Hopefully you'll get some extra practice with the homework, but like always, if you do have any questions about anything, please don't hesitate to let me know.